as some people have said, we're training some of these data centers to give an answer that sounds right, and that's not the same thing as giving the right answer. So
Fluency is
there's
not
some
intelligence.
concerns.
Unfortunately, in my university years, I had one example of a fellow student confidently talking absolute bullshit to our linear algebra professor. And he had to stop the student and say, wait a second. I appreciate your confidence, but please don't be so confident when you don't know anything. I am, as a professor, start questioning my own knowledge. You're so confidently speaking. And, it's like, it sounds much funny in Russian, but essentially that's what reminds me of LLM right now. It's a new
Do you worry?
reincarnation. We're on.
Hello, Ruslan.
Hi, Terry. Really glad to see you.
Well, it's good to see you. It's good to see you. It's nice talking again. So we've had some nice chats in the past, and always enjoy time spent with you. You were just telling me a little bit about yourself. I was wondering if you could tell a little bit more about what you find important in terms of software and people. You're a software developer of considerable background and some very interesting projects you've done in the past. So, what is your take on where the world should go with software and with humans?
Well, I mean, if you look at the whole point of computers, we have very synergetic potential with computers. So humans great at understanding the world, abstract thinking, conceptual reasoning, and at the same time, computers are much faster at calculating, processing huge amount of data. There is a great potential for that synergy. So we can work together very closely, and essentially, computers can help us to accelerate and improve our cognitive abilities and actually stay on top of what right now we can see as a cognitive explosions. So complexity of our world and amount of information and knowledge we have to deal with probably exceeds everyone's mental capacity. So we essentially operating in cognitive overload, and computers could come and help us. The only question is, can they understand us to be helpful? Think of, let's say, if you're a leader of the company, you have some technical assistants working for you. Because let's say Satya Nadella or any other CEO of the company cannot understand every potential technological aspect of his company developing. He needs helpers. He needs people who probably postdoc level, who can actually specialize in some areas and then kind of summarize and bring it for Satya and essentially recommend some decisions, right? But what it's actually super important for those assistants to be fully understood and understandable, and at the same time, they have to be accurate. They cannot essentially provide incorrect information for the decision maker. So ideally, we want to have this kind of assistance, thought partnerships for every human being. Because it's not just CEO of the company who needs this kind of cognitive boost, it's everyone. And it actually impacts the society as well. Because let's say a lot of people right now talk about AI as something which will displace the jobs, terminate the jobs. Do we actually need job terminator? Or we need someone who can help us be more productive and more stable as a society. So I hope that that will be the direction of AI industry eventually will take. Currently, we're actually running probably their own AI race. We're spending trillions of dollars and watching our energy bills skyrocketing, including mine. I'm not an exception here. But at the same time, it's kind of hard to see what kind of return on investment we're going to get out of all this. And I think at some point it will lead to some rude awakening for all of us, for our economy, for our society. So we should correct that and try to invest it in something which actually will bring really tangible results. Because let's look at human history. Humanity prospered because of innovations, because of technological process. Let's say even agricultural nitrates, all of this agriculture industry progress allowed us to focus more on the factory production. Because if before we have to also had to be farming all of us, simply just to stay alive. Now we have some excess workforce capacity to actually do something else. And the same happened with intellectual revolution. So we definitely solve our previous existential problems with technological developments, with scientific endeavors and whatever else in the same magnitude, right? Are we doing the same way? Is our scientific progress stolen, or we still kind of on an exponential trajectory? I think we pretty much stalled in most of the areas. If you look at hypersonic flights or like supersonic flights, we had Concorde flying no more. We used to have that. We have Mach 3 point pretty much 5, I can say that, I guess, flying in 60s. And since then, we haven't really developed anything more significant. When did we first launch the first man in space? When did we walk on the moon? Not recently, really. So our progress kind of slowed down. And I think we need to significantly accelerate what we have if you want to really be not just relevant, but if you want to survive in many ways. Unless we want to go to the Stone Age, I think we have no alternative but try to, establish the premise of science and technology again as a solver of all our existential problems. I understand Elon Musk is trying to say, screw the Earth, let's fly on Mars. But is it a realistic option for most of us? Probably not. So let's try to fix what we have here on Earth.
Now, one of the things you mentioned is the synergy between computers and humans, and that is a topic that has fascinated me for years. And I very much, I really like the way you phrase that about how computer technology can help us to be more of what we could be as humans, as opposed to displacing us, as opposed to just kind of removing our jobs, instead amplifying our ability. So, what do you think about this issue? Positive assistance with computers of the kind of intelligence that we have. Do you also see the possibility of negative additions in which the computer essentially works against us instead of for us? What do you think about that? Is
Well, I
this
mean,
how does this balance work out?
yeah, I mean, the thing is, what I think is very important is to understand the power of even the current AI tools. They still don't understand the world. They still don't understand us. But humans are humans, and we tend to over rely on things. So, for example, let's say many people cannot do mental math anymore since they have smartphones and calculators at their fingertips. So, ideally, the real AI, which we have to build, which should be human friendly, should watch for that human tendency and make sure that humans do not outsource their critical thinking. That's a big danger, especially for younger generation. Because let's say if you're already an expert and you know what the right answer should be, you can at least see that LLM hallucinating and giving correct results. But if you're just a young person who don't know anything or you're not specialized in that area, well, you have to take any LLM outputs with some grain of salt and try to apply at least first principle thinking and see if what it reports kind of makes sense. Without it, if you just train yourself to trust output, and humans kind of have that bias. Let's say if it looks good enough, you simply just click a yes button. So even if you're putting human in a loop in many safety critical systems, you will have to have that kind of bias towards just clicking yes. Because if your computer consistently right 99% of the time, you'll probably click 100 times yes, and probably miss that 1% was actually very critical. So the way
I
how we,
remember, I remember once when I was riding in a very early automated vehicle on really rough terrain. It's not the easy routes that they take in this. This was a research vehicle, and I was astonished at how quickly came to trust the vehicle, which was actually quite dangerous because we were going over hills, ravines. A misstep at any point could have been literally fatal to the entire crew who was on that thing. But because the vehicle made good decisions for the most part, it was so easy just to lay back and trust it and start assuming everything was okay. So there's this interesting thing about mostly correct is not necessarily the same thing as safe. And that kind of hit home with me as I was thinking about my own experiences with that early robotic vehicle.
one of the problem is humans and current machine learning models make different type of mistakes. Humans do have, and I hate to use overloaded terms, but world model becomes one of the overloaded terms. It means many things for many people, but let's assume, humans, they think in mental models. Humans can create a mental model of the world or situation around them. So let's say when you have that mental model, you could potentially predict what will happen in many situations. You don't have to have that much of a training data. If I lift that mouse and drop it, it's going to drop on the table. It's in your mental model. You don't need potentially too many examples of that for your training set. If you operate in a different terrain and you understand it, you're on an inclined hill, whatever, you understand at what point your vehicle can lose balance and fall and stuff like this. For humans, having that understanding can leverage, they can navigate novelty, they can navigate edge cases, which may not be present in many training sets your model will be trained on. Machine learning based approaches, be it computer vision or reinforcement learning, or worse, probably end to end machine learning, they do not have that kind of world understanding abilities. So they don't
That
know
that
what they're on, essentially.
that that topic you mentioned about how you put it into a different environment, one of the issues that we had with robotic vehicles was that you could train them extensively for, say, a particular desert terrain. And that desert terrain might look identical to everybody from a human perspective, except for people maybe who are familiar with the environment. But you put the environment, you take that that robotic vehicle and put it into another desert environment, and it would simply stop functioning. So there was a fragility of training that was hard even to define. So you wonder sometimes, we think we've optimized some of these systems for maximum effectiveness, but they tend to be very fragile.
Yeah, and even let's say from my experience at Cruise, so Cruise was self-driving car company, and I was working at behavioral foundation team. And what was interesting, we have to transition from San Francisco to some other cities, let's say Austin, some other metro areas. And what was interesting, even sound of emergency vehicles are different. The way how
Yes.
siren sound is pretty much identical for the human ears. We know it's an emergency vehicle, but machine learning model does not. You have to retrain the model for every city. You have to make sure that
Yes.
the look of emergency vehicles, the way how they sound, has to be incorporated in new model. The models has to be fine-tuned for that because otherwise it doesn't really understand many things.
That's fascinating because we were doing the same problem for desert environments and the same situation. There were small subtleties that just did not register. The plants looked a little different. The types of rocks looked a little different. The average grade of the terrain would be a little different. And you would think that would, as humans, we don't think that makes a big difference. And yet, for these automated systems, that has been a persistent problem that there's this fragility to it. I'm going to play devil's advocate for us for a second here. Jeffrey Hinton is adamant that the reason why we can trust large language models is because they work exactly the same way that humans do. In his perspective, when you train a large language model, you're doing a connectionist type of memory, and then that is the same thing that the robots are doing. Therefore, they should have the same result. Do you think that what do you think about that? What do you think about that idea that we are just a connectionist model and that all these things that we're talking about are achievable using this connectionist type of model?
Well, I mean, the thing is, let's say I don't subscribe to the same point of view. First of all, if it's to talk about brain mechanics, so there is this some good examples of bionic approach. So, for example, we observe the birds fly, and without understanding full aerodynamics, we just try to copy the airfoil surface, and then suddenly we get airplane. More or less, it's not the same. It doesn't have the wing flapping abilities. It's still probably less efficient in many modes of operation, but it can fly fast and it can deliver loads or whatever. Right. With brains, I think the process is much more complex. We still don't understand fully how cognition works at very low level. And let's say if we look at the model of perceptron, which is a foundational building block of artificial neural networks, that's fairly foundational, outdated model of human neurons from 1950s. It's very oversimplified and losing all electrical signals. The new research suggests that we have optical path also, we have quantum entanglement potentially involved. Ignore all of this. So we're just saying, look, we're just going to throw a bunch of those perceptrons, simplified neural model, network, artificial neural networks together, and suddenly at some scale we get human level cognition. Although we cannot really answer because the same neurons used in fireflies, used in rats, orcas, elephants, if you look at the brain mass, elephants much bigger. If you look at interconnectivity between neurons, orca is a chimpanzee there. At the same time, we don't know why human cognitive ability is so different. Because yes, nobody denies that rat actually intelligent animal, but rat eat our garbage and then we walk on the moon. There is some significant difference why we are capable of doing so. And I don't think connectionist model can actually provide any answers why, what, and what's the difference. Also, I'm not even sure if we know if we copy in the right side, because are we sure that intelligence fully concentrated in one human brain? Maybe entire body involved. Maybe you have collective intelligence when humans, when they're thinking in a group, let's say if you live with your spouse for a long time, you may be able to actually think alike. You can say the same words at the same time. How does it happen? Well, We don't really know. And then there is a religious aspect. So when people believe that some great ideas come from some higher power or whatever, and they get inspired by that. So the question is, are we copying a web browser or are we copying a backend infrastructure behind it? If you're just focusing on a web browser, that may be fairly dumb terminal. You may not get the entire infrastructure which actually has the real intelligence, right? So in this case, look, we don't really understand what we do, but we hope that we throw trillions of dollars into this and we scale it to enormous degrees and consume 90 whatever percent of human electricity. Suddenly we'll get that super intelligence which will solve our problems. Well, how realistic is that bet? I'll let you decide.
One of the one of the points that, and this has been a point of interest on me for a very long time, is the incredible energy efficiency of human brains of any kind of biological neural systems in terms of coming to simple conclusions, often very robust conclusions, one that allow the organism to survive. Compare that energy efficiency to what we're trying to do with these gigantic farms. And it's really quite amazing because whatever the neurons in a gnat are doing is not what's going on in some of these giant server farms, because that gnat can navigate small situations that would be extremely energy expensive for that server farm, just on a one-to-one comparison. So at some point, adding this energy efficiency issue seems to be an important part of that. Exactly what the resolution of that, I think, is that's part of the problem is we don't seem to understand the resolution. When we just skip over that and say, doesn't matter, that's not a very satisfying answer. We should be poking at mysteries like that, say, where does this go?
Yeah, and the thing is, what we also kind of forget that not every intelligence can live in a huge data center. So first of all, yes, we are probably wasting a lot of energy at this moment. We're probably not going to see a lot of return on that. Well, some funny videos, cartoons, maybe some text generated, some funny jokes, whatever. Yeah, that's fantastic. But in real productivity, are we going to have something more than work slop? Probably a big question. And even Satya Nadella and World Economic Forum recently was kind of asking to help to find a clear killer application for artificial
Yes,
intelligence
yeah,
because
saw that.
right now he doesn't seems to be see one, right? And that's kind of concerning by itself. But then there are a lot of things which has to happen at the edge. So recently I was at DARPA conference, and I have to assert that unfortunately the AI and AI race we participating in, building that intelligence, the huge data centers, is not going to benefit a warfighter in a field environment. Simply, you will not have connectivity to that great brain power somewhere far away in faraway land. So at that moment, you have to have something really close to the edge. Unless you have that, that's pretty much useless for many things. Robotics, at the same time, latency is not going to go away. So you have to make decisions in the vehicles, in the flying drones, in whatever, essentially in milliseconds. And unless it happens locally or very close to it, you're not going to get much of a benefit of this for huge areas of our economy or society.
Like your point about latency, because, and I think in everyday life, it's easy to miss this point because we think of computer systems as being very fast. And you say speed of light, you can go around the world 7 times in a fraction of a second. But when you have systems that are responding in real time to extremely fast threats, such as what you get in military situations, those differences become enormous. And a tiny increase in how quickly you respond makes all the difference in the world and whether you're successful in responding or not. And it's competitive. If the other system can respond 25% faster than you can, guess what? The other system wins. So I think you make a very good point about this whole issue of where is that processing power out at and how remote can it be. There's also the connectivity issue because if you try to tie your entire system, it could be an organization, it could be your company, it could be a military, you try to tie it in real time to a single computer, then you are subject to disconnection at any point. If you're doing from a military viewpoint, you would say that would be what you would attack. You would attack the connectivity. You'd say, I don't care how smart the server center is. If I cut it off, then they have no connection with that. So I like your point about how important it is that you have local ability to do that. And this also gets back to that low energy issue. You can't use all that energy in every device that you have. And also, it doesn't seem necessary because again, living organisms clearly do vastly better. And yet, that's a side of the research we haven't been doing as much.
Another important part is adaptability. So let's say, the fighter pilots, the Colonel Boyd, they have this ODA loop. I'm not sure if I'm
Yeah.
pronouncing it correctly, but essentially,
UDA, yeah. Yeah, yes. Yeah. You either spell out the acronym or UDA. UDA is often what I've heard.
yeah. So and essentially that applies not just for fighter pilots, it applies for any competitive environment. So for example, we face it at cruise as well. At some point, you need to collect a lot of additional data to train a model. So let's say you have to train it for a new city. You have to train it for edge case environment. So for example, you drive in a vehicle and someone carries a tree on the on the kind of let's say inside your truck or whatever, right? So suddenly, used to the fact that trees are stationary and suddenly the tree is moving, but it's a moving in a vehicle. Well, it may confuse your system because it may apply phantom braking because it suddenly see a tree in front of you. Well, you have to adjust for the fact that the tree is moving with the vehicle, so it's not a threat of collision anymore, right? But having that data, collecting that, is actually quite time-consuming task, especially if event is rare. Or, for example, let's say an elephant escape from a zoo and start walking in the streets. How often does that happen? Well, or let's say you drive around private jets. That's also not very frequent event, and Tesla was caught on it. Someone in the air show called the Tesla to self-drive and pick up because he wants to show off in front of his friends, and Tesla just ran straight into $3 million private jet because it's never seen private jet in this training set, and it doesn't have a concept that actually may collide with it. All right, so imagine you in any situation you have to deal with novelty. Let's say you encountered a new adversarial drone or whatever you have to deal with. Right now, for example, Palantir set up a special data room with Ukrainians to collect more data about Shaheeds and other Russian drones so they can train the AI models for interceptors. But the fact that it takes so long gives your adversaries chance to do a lot of damage for you and for your infrastructure, whatever, right? So basically, ideally, you want to have an AI which can adopt in real time, preferably in real time. And you definitely don't need a model which takes 30 or 60 days to retrain. And sometimes that's what we see at cruise, because let's say if your model become large and complex, you can improve certain things. So for example, we were fighting a long time for improving passenger pickup. Because in some cases, you approach the car in the wrong angle and cars start running away from you. So you hail, that's your ride, it's arrived. You're walking towards it and running away from you because you need to know with each angle to approach. Okay, you can change your enforcement model. You can potentially adjust that behavior, but then there is a side effect. It actually may be closer to pedestrian during normal cornering than you want. So you essentially regress in one safety aspect to improve passenger pickup. You don't want to do that. So can you train a model which does both reasonably well? Well, it takes time, and you have
That's
to
what
iterate.
That's one of the areas that I worry about most is because we talk about training and we saw this in the fragility of the systems. If you assume an incredibly large training set, you can train for all these different options, but it just becomes so imposing to come up with every scenario they could possibly come up with. You essentially have to work out how the universe is going to operate ahead of time. And that's just not feasible. Even with the size of these data centers, you still are going to get cases where you wind up not knowing ahead of time what would be a good choice. And those are the very areas where you see. I remember seeing just today, I saw an example where one of the latest chatbots was simply asked, draw a map of the United States. And this has become a meme on the internet. If you ask an AI, you ask the one that they claim are PhD level to do that, you have this problem that they almost invariably just kind of go nuts, and they just start doing all sorts of things, and it is correct to say that that is not the major intended use of that. But any human, if you had a human who was doing your taxes and you asked that human, "Could draw me a map of the United States," and they drew something that had strange creatures running around on it, you would be you would be remiss not to worry about how they were doing your taxes. So, just because you can't see the errors doesn't mean the errors aren't being committed. And this really greatly concerns me because, as some people have said, we're training some of these data centers to give an answer that sounds right, and that's not the same thing as giving the right answer. So
Fluency is
there's
not
some
intelligence.
concerns.
Unfortunately, in my university years, I had one example of a fellow student confidently talking absolute bullshit to our linear algebra professor. And he had to stop the student and say, wait a second. I appreciate your confidence. but please don't be so confident when you don't know anything, because I am, as a professor, start questioning my own knowledge. You're so confidently speaking, and like it sounds much funny in Russian, but essentially that's what reminds me of LLM right now. It's a new
Do you worry
reincarnation of that student.
do you worry about the time attrition issue? Because one of the problems is if a machine, and of course LLMs are notorious for speaking very confidently about everything. It's a habit that goes back decades to the papers that AI students wrote. They were just that was a style everyone used, and it bled right over into the population at large when they started getting deploying these systems everywhere. But you have this confidence, and then you say, well, is that confidence justified or not? And then you can spend, and I have done this. I think, oh, this might be a legitimate thing. And then I find out, oh, that was AI generated. And when I go into the details, I just find out that I wasted my time because it was a loose connection. It was could be good as an inspiration maybe, but without the rigorous backup to check out the idea, it was essentially a waste of time. And I worry about the attrition of human thought, the fact that we could just wear ourselves out trying to come up with the right prompt to get a trivial bit of information about how to draw a map correctly, how to
It's
get the correct
interesting.
set of numbers.
Currently, you kind of we circle to the problem work slope, and it's interesting. I recently attended NeuroIPS in San Diego, and I think just yesterday it was a study coming up that at least 100 references in the papers which were submitted and accepted at the conference were hallucinated, and significant
Why?
portion of those studies were
That's a
created by
lot.
AI.
Oh gosh.
So
That's
essentially,
scary.
yeah,
That's
essentially what
scary.
it means that now science become endangered because you don't necessarily see original thoughts in many of those works. You need to publish because that's how you get evaluated. And to publish, use generative AI. Generative AI generate your article, maybe with some input, but technically taking something else and even hallucinating the references. And
Oh
someone
my.
else has to spend their time to actually understand it. Maybe they also use an AI to summarize it back.
Yeah. In many ways, it's like a slow burning fuse because when you put a false result into a paper, especially one that has prestige and that people assume it's been well verified, but then it turns out to be a hallucination. The trouble is, how far can that get? Because even just before computers, you can find errors that have persisted in decades or even centuries that would just by word of mouth. Someone quoted something at some time, and then that got carried over. So that's just without computer technology. What happens if we have computers that actively amplify
That
that
amplifies it.
kind of carryover? Well, the consequences, that's the slow burning fuse part. Eventually, when you try to apply it, when you try to use it, when you assume it's correct, whether it's in medicine, whether it's in commercial, it's in finances, it pretty much doesn't matter. It's going to blow up and you're going to have a big problem, and then you'll find out what it was is, oh, this the ancestry of this thing was false. It didn't come from anywhere. So it's kind of terrifying. It
Yeah.
sounds like almost humorous, but then when you think about the consequences, especially like for something like medicine, I mean, goodness, just the consequences are terrifying of what you could do. Automated vehicles, same thing again. If you
Yeah.
start getting papers that are quoted, says this paper says that this vehicle works perfectly, but it doesn't.
Well,
Oh,
aviation,
wow.
look at recent Boeing scandals, right? So suddenly you trust the company verify your own product for official certification, and you don't assume that they can cheat willingly or not. So, the thing is, even before generative AI, scientific and engineering integrity was already under assault from the money, from the financial interest, from many other things. And now we just accelerate that tendency and make it much more dangerous, because now people can commit these things without even thinking about it. So it doesn't have to be deliberate. They just decide to use LLM because they need to publish something sooner. All right.
The paper. Going back to a different topic you mentioned, you talked about how people, when they know each other well, they can get into a mode where they can essentially, it's not so much reading their mind, but they can understand each other's signals so well that they work together very closely. This is a theme I've heard repeated all my life for software. The most effective software development teams are always the small teams. And the difference is that in a small team, unlike a larger team, you can get that kind of a synergy working. So two or three people can understand each other's code, understand each other's signals in ways that they don't. An example I always know from the from deaf community, sign language community, is deaf couples can get to know each other so well, and of course they're used to small communication using body language and facial language that it's very dangerous to play cards with a deaf couple because they will know exactly what's going on. There's a level of communication that really truly comes over as almost telepathic. You can verify it's not telepathic because all you have to do is block their view of each other and it disappears. But it's still it's an amazing and we don't do that with machines. We don't seem to have any idea how that works at the machine level. I don't think. Maybe some people would claim that's true with pattern recognition, but so what do you think about this close communication? What is that a distinguishing feature of human communication?
Well, I mean,
Is it
what is, I think the real important part is not so much the way how we communicate, but with whom we communicate. So, if you look at history of human computer intelligence, the fact that we have software developers as a profession, is the fact that computers don't understand us. Because ideally, it should understand us directly. You don't need to have people who has to create some user interface specially because, most of the humans will not be able to understand computer programming language or whatever. So they have to create some different abstractions, some different modality for them to communicate. But if you look at the history, we started with terminals, right? And we have GUI, graphical user interface, to create some kind of document analogy. You have folders, you have files, whatever. And still, we don't have the perfect synergy and perfect understanding with the computer. So we went further. We went to direct and touch interface. So you can actually move something on your screen. Okay, that actually creates a little bit better abstraction for some. Then you have virtual reality. And some people say, okay, Neuralink is going to be all. And it still doesn't help because the other side does not understand. And what was fascinating to me, and actually LLMs do validate it, if the other side shows even a little bit of understanding or even illusion of understanding, we're willing to come back to very old textual interface, which is not that intuitive. There's no touch, there is no speech, whatever. But we're willing to do that. It's like teenagers, the teenager will write a message to his girlfriend or whatever on SMS in a phone and still willing to do that because he hoped that the other person will understand and reply. And we have the same kind of human hope to whatever we communicate with. So the problem is LLMs do create that false hope. So what we need an intelligence which understand the world really and understand humans as a consequence of that. And then we would be able to establish much more understanding communication. Eventually it becomes more efficient and eventually we become like, in a way like a couple. But for that, AI has to be personalized for you. It cannot be just one AI living in a data center which doesn't know about you and it's just a generic model applied to you. Because let's face it, if we have friends, friends understand us much better. We don't have to start from ground up because we know what they know. We know our positions. They're probably fairly close. And if they're not, you know what they are. So you can have very compressed communication, very flexible communication with the friends who can understand it much easier. So let's say, and actually not just friends, even communities, let's say fighter pilots, they develop their own language. I'm never flying a plane or whatever, but you watch the movie 12 O'Clock High or whatever. 12 O'Clock High means nothing for me as a civilian, but for bomber or fighter pilot means everything. So they can compress information. They can develop their own language, etc., sub-language, which optimize for what they're trying to do. Ideally, you want AI which becomes your personal friend, your personal thought partner.
One of the examples that is most interested me in LLMs, because it's easy to come up with examples where something bad happens, like say, ask it to draw a map for you. You don't have to go far. You don't have to go far at all. And that's in the most advanced models. This is not something from 4 years ago. It actually seems to have gotten worse. I was struck. I saw the example of give a list of animals, and the one from 2 years ago was better than the one that from just a month ago on a more advanced system. Now think about that. That's very strange. The more advanced one was giving just random noise in some cases, didn't even have the text and the images aligned. It was actually drifting farther from reality than the other one. Again, this was a very, very simple prompt. And humans just don't do that.
There are a
So,
couple of explanations for that.
that's a negative side. And but the positive side was the example I was thinking of is Terence Tao, the great mathematician. He has trained his own expert system. I think part of what's happened here in expert system, LLM, I'm dating myself. He's trained his LLM so that it understands him. So he's got that communication essentially with himself through reflexive intelligence in which, he's bouncing off against himself, but getting computer assistance. And I trust him when he says that this is proven to be a real asset and actually has some theorem proving capability. But I think that's because he's replicating himself into that model. He's trained it sufficiently and kept it focused to do that. But you think about that. How many Terrence Towels are there in this world? Well, the answer is
Yeah,
like,
and if you
yeah,
look
not
at
many, not many. So you have to have a lot of discipline, and a lot of knowledge in order to enforce that because he knows what a false theorem is. He knows what a good theorem is. He knows an enormous, more than 999% of humanity, what is and is not reasonable. And for that reason, he can take an LLM and train it and make it useful and make it do really good things. So a
yeah,
Nobel Prize in chemistry, protein folding, same kind of thing, focusing in that. What do you
if
think
you look,
about
yeah,
those?
if you look at Terry's example, from what I understood, and it was discussed in NeuroAPS, it was actually a neurosymbolic system. So he
Oh,
used
okay.
LLM to generate a formal proof mathematical language. So I forgot the name exactly, is it Meta or something? So there is a mathematical language which actually designed for theorem proving.
Yes.
So he actually used LLM to generate statement in that language and then use theorem prover to see if that's actually correct or not. And if you cycle it multiple times, you can actually may get interesting results. So essentially what he built was essentially neurosymbolic system, which use logical based AI as well as LLMs together as a complex, as a
Oh, that
system.
yeah, that's interesting. I did not realize I'd seen another example of something similar, but it was another mathematician. But that makes sense because one of the things LLM is good at is giving these hints and suggestions and ideas and paths. Hands down, it does do that. Sometimes it gives really crazy suggestions, but it certainly can connect you into ideas and different ways of thinking of it. So if someone like Terence Tao is backing it up with symbolic reasoning, in which it's going on saying, okay, yeah, those are the ideas, but let's wrap that in, constrain it, make it fit. That makes sense. That iteration in that sense could be a powerful
And the
tool.
good thing is, formal reasoners, they can actually detect when something is not generated correctly. So it's like you have a validator and LLM output. If it doesn't generate something correctly, you can actually cycle it again and try to regenerate it. It doesn't guarantee perfect results, but at least in that sense, you can see some acceleration for your work. That's for sure. If you look about negative examples, there are several things which actually may be happening. So first of all, models do collapse when they train more and more on and more LLMs produce the content. Now, probably 50% of the images on the internet or videos on YouTube are also AI generated. You start essentially cycling models on itself, and it actually proven to be leading to model collapse. That's one aspect. The other one is humans. So my daughter, she's an artist, and she kind of involves in artistic community, computer graphics. They actually deliver specially crafted images to confirms and make sure they don't produce images correctly. And we see that at Cruise as well. So, for example,
There's
one
a
of the
market for this. I
yeah,
didn't
yeah, I mean, the
realize.
thing is, Cruise also face the same problem. So, for example, you're trying to take a job from Uber drivers. Maybe it's a side hustle for them, but they're not happy with you. So it was a movement in San Francisco to put, those traffic cones on the hood of the vehicle. And vehicle cannot maneuver because it doesn't matter how it moves, it still see a cone. So it decided to paint itself in a corner and just stop. It stop
Oh
moving.
my.
Cannot do anything. Humans can actually, so let's say, if you don't play nicely with humans, if you don't create some kind of positive relationship, will sabotage you. What recently was proven that it doesn't take too much to spoil, let's say, vibe coding models. So you can publish a product for authentication on GitHub. You can engineer 40, 50 positive usages, feedbacks, and pulls from GitHub. Suddenly, your vibe coding tool can pick up that module. And later on, you replace it with some harmful content and suddenly potentially pollute thousands of other projects. So people do it intentionally, sometimes for monetary gains, sometimes because they hate LLM so much.
Well, now
So
what one thing that worries me about that, and I know it worries you also because you also have military background like I do, that red teaming. If you say, "How do I want to take down someone else's system?" and you look at LLM systems and you say, "Oh, they built their whole network on an LLM. Wonder how I could pollute that LLM so that it starts giving either irrational results or nonsensical results or even results that might favor what I want to do." There was the example of the seahorse emoji is a beautiful example. That was with the latest, I won't try to guess which model it was, but seahorse emoji. You ask the chat bot, is there a seahorse emoji? And the chat bot would go on for about 15 minutes and then shut down as it went crazy trying to figure out whether there's a seahorse emoji. There isn't. But that was the problem, is it thought there was, and the reason it thought there was because of one conversation with it didn't have that many posts, but a few people talked about it and they were absolutely certain there was a seahorse emoji. And that certainty drifted over into the model and polluted the entire model on that point. Now, in terms of fragility, in terms of danger, if you're in an environment in which you have hostile adversaries going after you, if you have other businesses who want to destroy your business, if you have somebody who just doesn't like you, if you're talking about international things, the ramifications of that kind of fragility are terrifying, and I don't think get enough conversation.
Yeah, the thing is, on EuroPS, Missy Collins, whom you know very well,
Yes.
uh, presented a paper about forbidding the use of generative AI in weapon control systems of any side. And it was some lively discussions, but I was surprised she's the only one. So I fully support what she does and fully support her effort. What shocks me that not so many people kind of understand that
What
this is extremely dangerous.
one of the things that this has puzzled me for a long time, and until I saw Jeffrey Hinton talking at a recent conference, I didn't understand that part of the genesis is that you have a Nobel laureate who has just superb confidence, absolute confidence that these systems are perfectly capable of reproducing every behavior of a human being. And I had not realized that before. I did not realize that Dr. Hinton was that dedicated to the connections view from nice, that that's all you need is just the connections and everything it does it. So when you have folks talking so confidently and said, yes, 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 all we need to do is train it, and eventually it will suddenly correct itself. And that's the key issue. Will it correct itself? Because the
I
evidence is
don't
not
think
very
so.
good for that. I mean, if you look at the seahorse emoji and you look at all the fragility issues, it's quite the opposite. The self correction is not a conspicuous characteristic of any of these systems. If you have a human in the loop who's there to monitor constantly, like Terrence Tao, yes, you can get self correction and get something that's useful. But I'm surprised by that too. But I think part of it comes from you have some very smart people. And Hinton's book, I mean, he's written some. He is a marvelous algorithmist. He has made some just beautiful algorithms. A critical part of the team that came up with some of these methods. But that's not the same thing as a worldview. The idea that these systems will eventually become self-correcting is something I believe for most of my life. But we're not seeing the evidence of it. In fact, if anything, it's kind of the other way around. You see the simple queries are the ones that are the most dangerous, and the complex queries are the ones that work better. That sounds more like database retrieval. That's not the same thing.
I did talk to someone who knows Hinton fairly well. And again, I cannot verify it, but he was saying that one of the reasons Hinton resigned from Google was the fact that he cannot get rid of the training aspect because machine models have the training phase, right? Which humans do not. I applaud marketing departments of many companies who come up with very elegant terms and somewhat misleading because when we think about training we assume oh humans train as well, they go, they exercise, they
Right.
study in
Right.
university, but it's
Yes.
totally different type of training. It's nothing to do with human training, right? And the fact that he cannot make those models learn adaptively on the fly, and they do require that weight setting training process in a way, kind of what he told me that that what actually one of the reasons what discouraged Hinton from continuing his work at Google because he doesn't see the kind of exit from that. It's like a turn in your eye because you think that your universe will actually kind of converge on that vision that's essentially equivalent to biological intelligence, and training process and need for it essentially break that analogy, and you cannot solve it, and that drives you kind of unsatisfied in that way.
That's also why I was very surprised to see Hinton very recently. This was just, I think, the last few weeks. Give this adamant defense of the connectionist interpretation as being sufficient to explain all of human reasoning. And again, this is as you mentioned, this is a viewpoint that goes back to the 1950s, and it's a viewpoint that, uh, just as an example. I was at an annual research review, and the topic was bio-inspired memory. And I remember one of my comments was, I said, "I thought that was solved. I thought that was, the weighting of the connections of the neuron, and that's where the memory comes from." And that was my honest opinion up to that point. And we had several iterations were going around in this, and the bottom line was that a couple of very deep experimental neurologists kind of said, "No, we don't know what." They just kind of admit it. We don't really know what's going on. It's the standard line is that the weighted connections explains all of human memory because other ideas, and it's mostly by elimination because we it doesn't seem to be DNA. That seems like an unlikely path, but nobody it goes like, well, what is going on there? So it's almost like a default thing, and it certainly is part of it because you can train the neurons, you train the networks, they certainly have a memory. But when you get to these more complex issues about how to do something new. There's a lack of understanding, even of how basic memory works, about how we get the storage of the data. And that surprised me. And yet, that is one of the areas where we apparently need more research. We're not understanding some of this stuff. We've got some standard lines, but we don't necessarily have a well developed understanding of the deeper concept.
Interesting. At DARPA, I have to remind them of DARPA paper from 2017 defining the waves of AI. So the author of the paper at that moment said, okay, we have three waves of AI. So we have first wave, which is symbolic AI, and essentially it's executing the rules, and the rules likely have to be encoded manually. I would actually add wave zero, which is normal software, because in a way you can represent your knowledge in C++, Fortran, COBOL, whatever the language, right?
And
So it's prescriptive knowledge in a sense, but okay, we can call it wave zero or not. But then you have wave one, which is symbolic AI. And the problem with symbolic AI, it's kind of hard to represent essentially uncertainties. It's hard to represent some kind of intermediate states. Yes, you have fuzzy logic, but fuzzy logic
yeah,
collapse after a few inference steps, and you don't know what to make sense of those numbers anymore. So, all right, so then people give up on knowledge representation at that moment. They say, you know what, we cannot find a way to represent knowledge in somewhat meaningful way. Let's go to the wave two, which is machine learning, throw a bunch of neurons, and through training process we figure out some ways, and hopefully, I mean, it gave some significant boost. So computer vision models for what we have for like predictive analytics, for regressions, classification models, we definitely see some progress there, definitely. And of course the continuation of that path would be, okay, can we do more? Can we do for transformers and out encoders? Can we do LLMs? Can we get generative AI? And that's main area of investment right now. But then even at that moment, DARPA identified the third way, which they call cognitive AI. And cognitive AI is about adaptability, is about to essentially attempt to build more conceptual models, more generalized models, so you can actually learn more in a human way. And often in cognitive AI, you develop more sophisticated cognitive architectures. So if you talk about Kahneman, and his view of human cognition as fast and slow thinking. System one is fast and intuitive and sometimes wrong and often wrong. And system two is more deliberate, more correct. So let's say if you're working on theorem proving, that would be system two. Or even driving a car. Let's say if I drive car from my home to office, that would be most to system one. If it's a normal route, nothing has changed. But if some jerk jump in front of me or something unusual happen, let's say you have a road closure and you have to find a turn kind of reroute yourself and detour, then your system two will kick in and say, okay, what do I do now? So in many cases right now in wave two, you don't have much of a system two at all. So you focus on system one. So you cover, in case of humans probably use system one 90% of the time simply because it's more energy efficient. The thing is, it's true for our wet brain, and we have different type of brain mechanics. But if you talk about CPU and GPUs, calculating abilities of that is much better than human brain. So essentially, we may have a different split between system one and system two type reasoning in artificial intelligence. And at the same time, we ignore system two mostly. So for example, in autonomous vehicles right now, system two is a human remote operator. Not so many people know that typical self-driving car, every 4 to 5 miles, will connect human operator with question, what do I do now? So let's say you're stuck in a traffic jam, you stand and, at some point you think you're stuck for too long, you ask the operator, should I go left, should I go right? Tell me what should I do? So that's kind of unknown, and many humanoid robots doing the same. So there's a human operator somewhere behind. Okay, you may have like three cars for one operator, or four cars for one operator, or whatever it is, but there are quite a bit of humans at the back. And if those humans are not sufficient, say in San Francisco, you suddenly lose your traffic lights, and you cannot figure out what to do because it's not in your training set, then your human operators get overloaded and essentially your entire fleet shut down the streets of the city, which happens with Waymo recently, right? So basically, there is no real progress, especially in edge case handling, in novelty, unless we enhance system two capabilities of the current systems. And that's what cognitive AI is supposed to do. But it's not what people invest in right now. In cognitive AI, you can probably count neurosymbolic as part of cognitive, although they're not necessarily the same thing. Cognitives have much more sophisticated cognitive architecture. It has long short-term memory. It has metacognition, which is very important because it's supposed to monitor how it thinks and essentially correct its own thinking and kind of optimize the process of thinking and reasoning while doing the work or shortly after. So that's much more interesting direction of AI. But what I'm building, I would call the fourth way of AI. Because let's say you build an intelligent system which can solve, let's say, Tauro Hanoi problem. Let's say if your kid in a kindergarten show that kind of potential, that's great. But does it mean with certainty that that person becomes a great scientist, great engineer, or even great military commander? Well, it's a probability, but there is no certainty because at some point you move into representing much harder concepts. And the question is, would you be able to operate in this? Typical example would be the world model example, right? So if you look at Jan LeCun and many others who just right now switch into world models as what has to be the next step, the question is, what do they mean by world models? I mean, classically, it means that you create a model of the world. But what happens in many connectionists, they still trying to uh, bring it to connectionist world and try to construct and translate some kind of understanding of the world into multidimensional spaces, latent spaces, and then trying to tweak neural networks to take advantage of that and somehow become smarter. But I don't think it's substitution for entirely the way how system two will handle it. So, for example, typical example, the system I started building was early 90s. Essentially, the goal was to optimize development of weapon system in Soviet Union, space vehicles and their parts. And let's say if you take a ballistic missile or space missile, you have to solve dynamically systems of tens of thousands of partial differential equations to simulate how it flies. So I understand Tower of Hanoi is a very simple and discrete problem. You have discrete states. It's easy to simulate. If you go to much more complex systems, can you actually reason at that level? Because you not just need qualitative, but very extensive quantitative reasoning as well. Currently, ChatGPT cannot even calculate number of R's properly in strawberry versus raspberry. Still, ChatGPT 5.2 still suffers with that. And then
Has
we say,
amazing difficulties counting and adding. And the irony of that is that you have gigantic server farms whose essentially their fundamental operations consist of nothing but correctly, mostly adding numbers and multiplying numbers. And you put all of that computational power based on adding numbers to get a result that you say, could you tell me or count something or add some numbers? And it fails spectacularly. There's an efficiency issue that you got to look at here. You got to go like, there's got to be, which is why I like it when you said software is zero, AI zero, because
yeah,
software actually is very good at capturing cognition. It's just that it's limited in terms of the diversity of what it does, but it's
well,
powerful in
yeah.
that.
And
Now,
the thing
can you
is, yeah,
can you tell me a little bit about when you mention those problems, like all those differential equations? One of the things that one of the reasons I think why neural nets caught on was that many of the models that are more cognitively based in the past, there's scalability issues. Do you want to talk a little bit about scalability or add that aspect
yeah,
of it?
so basically, you do have, let's say, if you go more towards qualitative simulations, there is also an issue of infinite complexity. So let's say what we have to understand, and we have to copy not so much low-level brain mechanics of the humans, but how we represent the knowledge and how we approach our reasoning in different situations. So that's what we based our solution on. So, for example, if you look at mental models of the humans is actually you cannot really extract it properly. That's hidden and probably personalized for every particular brain of the human. But we have conceptual models. abstract conceptual models of all our science, physics, whatever. So if we look how we represent knowledge in science, that could be a good hint. Then we have different portions of philosophy and system engineering. So basically, we can essentially derive the way of describing this world, which is actually very similar to the way how we think, because we cannot necessarily, we should not replicate human level thinking, but we should at least create AI with human compatible thinking. So we should create AI which has to be a white box for humans to understand. And one of the reasons for like model based reasoning, you don't have to verify every calculations. You have to verify the models and assumption behind it. And if you believe that model and assumption behind it correct, you can trust computers to do number crunching. That actually would be, yes,
Yes.
CPUs have mistakes sometimes, but I remember the last time was Intel and it was a long time ago. So basically, usually that allows us to build much more robust and reliable system, which actually can verify and interpret results and have explainability at the level that we can trust the system. So that's one thing. Another thing in terms of complexity, if we look at our models and the way how science evolved, let's say we start as humans as a model as a flat. And there are still some people who proponent of flat Earth right now. That's fine. What is interesting, yes, we later decide that and prove that it's actually the Earth is spherical. And later on, we find out it's not spherical, it's geoid. And we can go on. But what is interesting that it does not invalidate entirely the flat Earth model. It just put a bounding box around it. So if you shoot an arrow 25 yards away, you don't have to care about curvature of the Earth. You don't have to complicate your calculations. And if you shoot at 100 yards as well, you don't have to worry about curvature of the Earth or Coriolis effect or anything like this. Even 300 yards, you don't have to worry about it. But let's say if you're shooting mile and a half away, you have to. So the trick is to not to dismiss every potential model. It's embrace all of them and then create a model for particular situation with the level of details, complexity, and precision you actually need for whatever trying to do.
It's interesting because what I'm getting as an image when you say that is a hierarchy of models that when you have a model that works very, very well for a particular context, and that context is where you're mostly living, where you're mostly at, then you use that model, but you have this ability to go to a broader model that then if you take care of the special cases, so you have this boundary point where you say, okay, it's time to switch over from Euclidean geometry of special relativity to the curved space model of general relativity is another example of that very much of that same kind of context. Newtonian physics works fantastic for most things we do. And yet, in our modern world, even our GPS would fail miserably if we did not have full general relativity, not just special, because you would wind up being told to turn at the wrong place if you didn't take gravitational time dilation into effect. I still find that amazing that just on a daily basis we encounter that kind of depth. So, so you see systems as like hierarchies, or I'm getting almost like a fractal map of some sort.
Yeah,
How would
so
you describe?
basically, essentially, we have to embrace multivariancy of models, multivariancy of ontologies. And it's like typical example, you can argue, is orca a mammal or is it a shark type fish? Well, technically, if you look at biologists, you say it's a mammal, right? But it has awful lot of features which make it shark-like, and it's probably as dangerous as shark if you, let's say, seal, whatever, both can eat you alive. So let's say if you try to preserve your seal, you probably should treat them as analogous in many ways. So the fact that we confound ourselves to hierarchical ontologies, that we cannot optimize it even at computational level. So basically, we would like to build a system which can do this kind of optimizations by itself. So you don't have to spend huge effort on ontologists who will, argue for decades how they should put certain relationship between the objects. No, it could be flexible enough for system to optimize itself and make sure that analogical reasoning flourishing in the system, right? And also, in terms of computational complexities, we have to have different types of models, different types of scientific laws with boundaries. And then, when we analyze particular situation for particular task, let's say you want to shoot something at 300 yards, we can then say, okay, which model shall we use? Yes, we probably have to take advantage, take a look at wind and maybe something else, but you don't you don't care about Coriolis effect, you don't care about relativity, you don't care about anything else. So you can simplify your models And then your simulation becomes very trivial in many ways. And if you think about, let's say, some high level process, let's say like airplane design, when someone design a new airplane, let's say, think of Scanwork or whatever, think at a table with his colleagues and say, okay, let's design how we can design a plane. It's over the napkin calculation most of the time. And they would use statistical models. They'll look at something like, okay, do we have any other planes which could be comparable to us? So if your customer saying that you need to have a plane which 90% payload compared to the weight of the plane, you can say, you know what, if you look at any other planes, we can probably be 50%, maximum 60. Now you're asking us to increase it that much. Can we actually do it? What differentiates us from Galaxy C5 or whatever? Why would you think that we would be able to do that? Do we have like new materials which more weightless, or do we have like I don't know, super efficient engines right now? So our propulsion system will take only 5% of the fuel or whatever. So basically, you can have that calculation, and that's a place for statistical based model, for machine learning models. Because yes, we can do computational fluid dynamics. But since we don't have the blueprint of the plane yet, we don't know its geometry, you cannot use that approach. Yes, you can do a finite element method to calculate the strengths of and validate the strengths of the plane, which are already kind of defined. But if it's not defined, you cannot really do that. You use mostly statisticals, you use analogies, right? So it doesn't mean that machine learning models or simplified models or approximated models, they do have their use, but they have to be used in scenarios when you don't really have certainty to do more precise models and you actually need that precision. But eventually, when you start detailing your plane, you decide your composition. You decide, is it going to be canard or normal wings, or it's going to be flying wing or whatever. So you can establish the more or less esquisse kind of look of your plane, and you define more and more and more. At some point, you'll have full plate defined, and then you can validate with $5 million CFD run to cut off on test flights or whatever. So you can do all of this, and you can unite all of this in one methodology and one artificial intelligence system, which will use whatever methods and models necessary at different levels of knowledge and certainty, and essentially computational effort you can spend as well.
One thing I like about that kind of model is when I think about my own cognitive approach to solving a problem. Initial approximations are very important, and I try to be more aware of that these days. Saying how am I solving a problem? What am I doing? And a lot of times, just a simple observation of what domain you're working in, about what kind of scale, or something that works, or you find something that works and then you try it again, and if it repeatedly works again, you focus in on that. So the idea that everything is fully resolved ahead of time is certainly not how humans seem to work. We have a much more complex and nuanced and also more tolerant. I mean, one of the things about solving a problem is you have to be tolerant and say, I don't know even why this works. Most of the great inventions of human history, the explanation for why it worked came a lot later, not necessarily ahead of time. So we often have this image. I think science may inadvertently kind of promote or intentionally promote it, that the theory comes first and the applications come next. That's true in the sense of the expansion of the application, but in terms of where the idea comes from, it's usually the other way around. Usually someone has some kind of innovative idea, they do an invention, they do a new technique, they have an insight, and then from that, there's an expansion, and that's where the rigor comes in with expansion once that idea is proved right. But so often it's a much sneakier path before you get to the full theory, and the full theory seldom emerges ahead of time, and when it does, often it's a theory that doesn't really predict that much. You can make elaborate networks, but they don't necessarily, say
Yeah,
that. Yeah.
and then another thing is at some point you get simplification of the
Mhm.
model. So, for example, finite element method is well
Mm.
defined
Yeah.
as well as strength analysis. But if you look at international building code, it doesn't go to a certain level of details. It says, okay, if you're using certain height of, 2 by 4 or whatever, 2 by 8 or whatever, you can have, and your span between the joist or whatever, between the foundations or whatever you brought in, then your spacing has to be that much because we assume certain load on the floor or whatever. So they're actually trying to come up with simplified models. So typical architect, a typical civil engineer doesn't have to run 3D modeling and finite element methods on top of it. So they're trying to reduce that computational complexity. The same as gearboxes. Let's say if you look at mostly engineering books about gearboxes, yes, you can analyze the teeth of the gearbox, let's say if it's spur gear with finite element method. But often they know the standard profiles of the teeth, and that's what probably you get anyway because you have standard equipment to manufacture it, whatever. So they just have the formulas, which helps you, very simple formulas, which help you to see if your tooth will break or not under which load, and how much reliability you get, how many hours or how many cycles that tooth will actually hold if it builds from certain materials. So the thing is, having the most precise models doesn't mean that's the end of the story. So then it gets simplified. So again, the cognitive or computation loads of people who using it get reduced to the point that it becomes very easy to use. So that's actually another interesting loop in terms of we're not just going for the most precise model. We essentially then correct the simplified model based on whatever latest discoveries from precise model. Normally, normal people can actually use it relatively simply. It's the same applies to AI. So basically, you don't have to modulate like gearbox at the quantum level. That would be a huge exercise, which is absolutely unnecessary. Right?
One of the things that strikes me about the application of LLM models is when they do come out with successful results, interesting results, like in some of the chemistry and the protein folding, a lot of times that complexity winds up turning into a simple rule, more like what you're talking about. And I do wonder if, in many cases, you could just then ditch the LLM and all of the data processing goes into that and translate what have they found into something more like what you're talking about. So I tend to think that even in the cases where LLMs are successful because they're great at going through masses of data, that certainly is one of the things they can do. But a lot of times, then they find a pattern, and that pattern may not be that complicated. There was a very recent report about how analyzing one night's sleep could help you diagnose disease. Haven't got to look at that more closely. I want to look at that paper because it's extraordinary claims require more examination. And yet, when they say things like, well, when things are out of sync with each other, that tends to indicate a problem of this sort. That actually makes a lot of sense to me because this is something that you got back in the old rule based systems, but you can also make them into much simpler computational structures than having that full setup. So LLMs as discovery mechanisms to go more towards a model of what you're talking about, where you wind up with a set of rules and you have hierarchies of how those apply. That intuitively makes sense. You mentioned fuzzy logic, and I have to mention that one thing is every time I look at the attention model now, I didn't do this when I first read it. First time I read the attention model paper, I thought that's very interesting. And it's somewhat mysterious. And yet, in retrospect, I'm going like, how is that different from fuzzy logic? All you're doing is discarding the lower probabilities. Yeah, I mean, if yes, there's a much more massive amount of data, but attention, by the very definition of the word, says, I'm only going to focus on what I think is important. And lo and behold, in many cases, that will give you a good, reasonable sounding answer. But I'm not sure that's that different from the fuzzy logic system. I actually built a fuzzy logic system on Prolog once. So this is an area that I remember. I remember it was interesting. I also remember it's hard to get them to work beyond about one or two levels. They tended to fail after that. And the information structures seem very shallow in much the same way. Nominally, they're deep, but you look at the transformers, and because of that discarding of information, it looks an awful lot like fuzzy logic. Ruslan, what are some of the things that you're working on right now that you're particularly interested in? Where do you think things should go, and what is your interest for the future in some
Yeah,
of
so
this?
basically, just to circle a little bit on fuzzy logic and on protein folding, AlphaFold, for example, that's a neurosymbolic system. So people
Yes,
say it's LLM, it's not.
they
It's
they,
much more
they
complex.
it was interesting how that happened because the first models of the protein folding successes did not use LLMs, and I think it was the third model, something there was this complicated history. There seems to have been some politicking for credit about who gets credit on that. But the first versions, the ones that had the real successes, were pre-LLM. They were not based on LLM as far as I know. I mean, if it's complicated history, but yeah, there is a more complicated thing going on with that. And that is, I've touted myself as an example where LLMs can be useful, but are they fundamental to what they did? I don't think so. And also protein folding. They do not understand protein folding. This is an amazing thing. People talk about solved protein folding. What they solved was the relationship between the DNA and the result. And what is still an unsolved problem to this day is how the folding actually happens, which is, I find that remarkable. So it was kind of a shortcut. And the reason that's important is if you get a difficult protein that's no one's seen before, it fails. It just falls apart. Why? Because it doesn't understand folding. So
Yeah, and
as
then
so
another
despite
another
the title,
interesting yeah, another interesting take is physical informed neural networks. Basically, the idea is, let's say, if we can create a neural networks which somehow approximate partial differential equations. So I've seen a recent example of this. Typically, people who are actually doing real modeling, they usually complain about pins and saying, they don't really work. Like 2025 triple AI, one of the gentlemen who was doing simulations for, well, mostly military applications, he was saying, look, Wachovia forms is much more promising. It can cut computational cost by 6x. Pins, we cannot really make it to work and produce reasonable results. Recently, NVIDIA released some models for computational fluid dynamics. So they will take an airplane wing of certain type, of certain shape, and they vary the angle of this between, let's say, 8 to 12 degrees or something, and a couple of more parameters. So they run hundreds of CFD simulations to create that model of kind of physical informed neural networks. So the idea is that you can spend energy for thousands of runs. And later on, if you design your own airplane, you can easily vary, let's say, the sweep angle of the wing. Let's say you want to have 8, 9, 10, 11, 12, and see which gives you better results for your particular airframe. And the calculation is that you will design many planes using that model. Because if you, I don't know, you spend hundreds of CFD cycles, which cost a lot of money, to create 2 or 3 or 4 planes, that may not make sense and not pay off. So, given analogy with protein folding, all the GPUs which used for, training of LLMs, what if they used for simulating physics of protein folding, maybe would get similar, better results. Still open question. So the same as here, right? So basically, if you change the profile of the wing, that may not work. If you change the composition of the plane, let's say if you switch to canard wing, oh, that may not work. So there are a lot of restrictions of the pin applications. It may be useful in some cases, but it's always a careful calculations. How many initial investments I have to do the runs, then to approximate it, and of course, there is error on top of what happens. So they claim to be about 1 to 2% extra error compared to CFD. CFD itself has about 10% error compared to real aerodynamic tests. And then you add 2 more. So it may help, it may be useful to consider more variations and potentially arrive to slightly more optimal design, but it's not a panacea in many ways. So we have to be always kind of be practical about what physical informed neural networks can do, what kind of mistakes they actually do. And you have to make sure that you bound the models very, it's like, you fence it in a way that you know the areas of duplicability and you know in which area error will explode. So you know what you can actually use it for, but not beyond that point if you need precision of exit.
I remember on some reviews, one of our favorite groups was Boston Dynamics because they were doing robots that nobody else was doing at that time. But the other thing that was striking about Boston Dynamics is that they were a skunk works outfit. And they proudly and without any equivocation said, "Yeah, we assume that we're wrong, but we build something, we try it and keep doing it." So instead of relying on a theory and assuming that some elaborate theory is the only way to do it, this idea of testing against reality is pretty powerful. And as a result of doing that, they were able to come out with mobility results for a variety of robots, not just the humanoid robots, but for all sorts of four-legged robots. Nobody was doing that at that time. Nobody. And a little bit of humility, really, seriously, was the main ingredient they needed. Is saying that, yeah, our models maybe aren't as good as we think they are. So I like that idea of we shouldn't overinvest in precision before we really know, because the universe is constantly fooling us. And
Yeah.
there've been so many cases where you get a good model, and that model kind of takes you down a path that you later find out was not a good one. And yet you don't know it because you're just following only the model. You're not listening carefully enough to what happens when you apply it. And that is something we do need to do. It's been great talking to you. Do you have any uh, parting comments, suggestions? Where do you think what do you think people should be focusing on? What do you want to focus on? What would you say?
So I would like to focus on, I would call a real super intelligence. And super is not just a marketing term. It has to be, semantic. It has to be sustainable. It has to be user focused. It has to be pragmatic. It has to be resource conscious and solving real tasks and it has to be ethical. That's what super means for me, right? Because basically just meaningless definition doesn't help. So we need to build a new AI for the next phase of our humanity. And that AI has to make sure that we not just improve everyone's else cognitive abilities. We want to make sure that we maintain social stability as well. So one of the big things, if I grew up in communist society, and the question was, should people own mean of production and whatever. So I would argue the AI and superintelligence I will build should be able to deliver it for everyone for free. And essentially, some basic knowledge will be available for everyone. Now, let's say if you want to go and study something and make sure that your AI knows, I don't know, stock trading or whatever, that could be some student loan or anything you can take which will help your AI be smarter and help you to become more specialized in certain areas, right? So basically, you're probably not going to have humanity knowledge for free. That's not going to happen for everyone. But you can still make it your thought partner in whatever you would like to do. And it will actually help you to be more prosperous, be a more useful member of society. I don't believe in general basic income or whatever it is touted for. So I don't like the philosophy when you have a bunch of useless people, which we shove them on drugs, video games, and universal basic income just to keep them quiet. No, I don't think they will be happy. I think people would like to still create, would like to feel good about their contribution to society. And I would like to build an AI which kind of enables that for people. And also, another thing, I think we can actually help to build successful consensus between elites and the normal people because currently, let's say, a lot of billionaires build in huge bunkers. And the reason why, essentially, you build in a prison for yourself. Do you want to lock yourself for life and be afraid to step out? Or be afraid of your own guards you hire? So they actually, if something really catastrophic happen in the world, you think you will be running your bunker. Or the guys with guns who's supposed to guard you will run you over. Why build society like this? Why can't we have a kind of Nash equilibrium somewhere so we can actually all be happier and more organic as a society itself. And I think that's what real AI can bring to the people, and I'm building it.
Very cool. I'm almost getting the impression like a public library of art of super intelligence, something that's accessible by everybody. That if they want to, I remember how important my public library in my small town was to me because I could go there and find out things that I could not have found out otherwise.
So in
So
our case, yeah, in our case, it's very simple. Let's say if you would like to share your knowledge for free, it will be delivered for everyone for free. If you would like to get compensated for your knowledge in a, let's say, form of acknowledgement, or you would like to get some percentage of future sales or whatever, that's fine. We can accommodate that. And at that point, we can, as App Store, take some cut from applications who want to be sold there. We can also take like 3% or whatever from the sale of your intellectual property you would like to sell. And let's say at some point you have a great idea. Maybe you want to tokenize it because it may bring profit 50 years from now, but you want that profit be maybe ahead of time so you can sell or tokenize your property and then essentially replacing many of aspects of the stock market today. But again, it's a ground, the stock market of ideas. It's not stock market of derivative speculations. So there is a difference. I'm not trying to blame anyone on the stock market and the financial sector. I'm trying to stay out of politics in that sense. But I think we can build a foundation for much more harmonious society. AI
I,
can help us.
I like the idea of hybrid models where you're saying if you want to donate something, you can donate. If you look at Linux, why does Linux work? Because you say, why did everybody contribute this for, all the work they did in it? Well, the reason was it gave you a result that everybody benefited from and no one person could have contributed to. And you take it out of the equation. You say, okay, we'll give some basic infrastructure, but then you compete on top of that. You can have your proprietary ideas. You can have a whole spectrum of things that you build on top of that. And the models are not exclusive to each other. In fact, in many ways, a company does not want to build their own operating system. That's a very, very poor business decision. Whereas if a bunch of companies cooperate and say, here's our shared infrastructure, now let's all get to it on competing. That's a powerful model because then you have that free market incentive. You have people say, "Hey, I can do better," but at the same time, you're not wasting your time just doing the same things over and over again. So I like your ideas in this, Ruslan. I like the idea of super intelligence as a resource for people instead of something that's just tied away. And I won't you won't hear me say this very often, but I actually feel sorry for those billionaires. That's a miserable, miserable worldview. Literally imprisoning yourself, cutting yourself off from humanity, cutting yourself off from basic people. I will point out one billionaire who has not done that. I don't necessarily agree with him on everything he does, but Bill Gates has put so much energy into helping on health issues and on actually doing real solid aid to people around the world. And so, you know, don't cut yourself off. Share what it is to be human and do that. And don't make yourself into a misery. Yeah, you can have a really fancy bunker. So what? It's still a prison. Why do you want to go to prison? Literally.
Bill Gates
Why?
was an interesting example. Let's say, we live in Seattle, and sometimes you can see him go into a local burger shop called Dick's, and
Oh,
he would stand in line with everybody else, and you don't see,
yeah.
battalion of guards around. So basically, there's something in this quality of life. So I would call all the billionaires just to see that there are other options, and they can help to build the system.
Yes.
So there is no
And
need for, so
there's
much
no
bank
need for
mentality.
there's no need for this friction and something like that. Rosalind, thank you very much. I
Thanks
really
a lot.
enjoyed talking to you, and I think we'll talk again at some time in the future.
Thank you. Absolutely.
Okay.
Thanks a lot, guys. Thank you.
Thank you.